guys, and welcome to HSC Chemistry and the Chemical Monitoring and Management Unit. In this particular video, we're going to focus in on water quality. The first thing to say about water quality is very much dependent on the purpose. There's a difference in water that is designed for human consumption, or water that is drinkable, which we call potable water, and, for example, the water that we might use for domestic use, such as cooking or cleaning, agriculture, and also for recreation, so boating sports, for fishing, for surfing, all of those sorts of things. So these are all different uses, and because they're different uses, then there are different conditions that, I guess, determine the quality of the water. For example, often where we do a lot of boating, there can be fuels that have been spilled into the water. And so whilst the water might be suitable for boating, it may not necessarily be suitable for fishing. The fish that are caught there may not be suitable for eating, and certainly for consumption may also get across. So, and something like hard water is something which is often not a suitable thing for domestic use. So if there's a high concentration of calcium ions or magnesium ions, these will make the water hard, and that makes it harder to lather, harder for soaps and detergents to actually produce a decent lather, which means if you're washing clothes or washing dishes or washing your hands, you just can't get a decent lather. So we want soft water for this sort of activity. So there's a couple of different types of activities that determine whether or not the water quality is sufficiently high for those particular purposes. For drinking water, so potable is water that is suitable for human consumption for drinking. It needs to be colourless and clear, so there needs to be clarity, typical of the water that we see coming out of our taps. There needs to be no odour, and there should be a relatively pleasant taste. There shouldn't be any sort of aftertastes or metallic tastes, anything like that. The salt concentration should be very low, not necessarily zero, but certainly very low. We shouldn't be able to taste salt in the water. And all pathogens should be removed, and the same thing for any dangerous or toxic chemicals. So that may include things like heavy metal ions, like lead, and anything else that's likely to cause some health-related issues. In the environment, the quality of the water doesn't need to be quite as high as it is for drinking water, but because there's a lot of organisms, they are going to need oxygen. So both the plants and the animals are going to need a supply of oxygen that's in the water in order to survive. So there needs to be dissolved oxygen, environmental water. We need to have a shortage of oxygen-consuming substances. So any, metals which may readily oxidize and draw oxygen out of the water will reduce the oxygen levels, and of course this is going to affect this group of organisms up here. It needs to be relatively free of suspended solids. Suspended solids comes into something we're going to look at later called turbidity, and this can be something simple as making the water darker, and that affects the light for photosynthesis. So if there's plants in the water and those plants can't receive light from the sun, they're not able to photosynthesize, and turbidity or suspended particles can actually affect them. The other problem we have is nitrates and phosphates. Now these often come from agricultural runoff, so the source is agriculture. The problem that they create is a problem of eutrophication. And if you think of eutrophication as basically we put nitrates and phosphates on our farmlands and our agricultural regions because the soil is poor and we want to grow crops, we want to grow plants, and plants grow better in high nitrate and phosphate conditions. So when we put those into the waterways, we're going to do the same thing. We're just going to grow more plants. The problem is the plants can actually choke the waterways, and often we get things like algal blooms, and these are a consequence of these nice rich nutrient-rich waters, and as a consequence they are not particularly good for some of these other things that we've talked about earlier on. So what sort of things do we test in order to determine the quality of water? Well, the first thing we need to look at is the concentration of common ions. So these will be things like sodium ions, chloride ions, calcium ions, and so on. We want to make sure that the concentration of these ions is, generally speaking, relatively low. Obviously, it's different for an ocean to what it is for fresh water, for drinking water. But we check the concentration of the common ions. We look at something called TDS, which is total dissolved solids. Now, that's generally speaking easily done just through evaporation, but we need to look at not just the type of ions that are present, but also how many in general are there. Water hardness, which specifically relates, as I said, to the presence of calcium and magnesium ions. Turbidity or clarity, and that's often related to the presence of suspended particles. Acidity, which we know is related to the pH. Dissolved oxygen, which is the amount of oxygen that is dissolved in a certain amount of water, and this is important for life forms who are going to use that oxygen for respiration. And also, so DO is often the abbreviation for dissolved oxygen, and biochemical oxygen demand, BOD. And this is basically the oxygen usage by organisms. So the biochemical oxygen demand is just literally that, the demand for oxygen. So if there's more organisms that are going to be taking that oxygen, then that's going to be a high number. So we need to test for each of these, and there's a lot of information on this slide. Don't worry too much about trying to memorize every single thing that's in here, but it's important that you make sure that you could have or describe one test for each of these 3, 4, 5, 6, 7 7 properties of water. Okay, each of these contributes to our discussion of the quality of water, and we want to make sure that we've got each of them covered. So as far as the concentration of common ions is concerned, this is where we're actually trying to identify them. So with cations, it's easy to use AAS, and you know how to describe the process of atomic absorption spectroscopy, and you've also carried out precipitation reactions for gravimetric analysis in identifying anions. Some values here for potable water, and you can see that those guidelines for iron, aluminium, manganese, and fluorine, very, very low. Those measures in parts per million, and obviously we don't want salty water for our drinking water. Total dissolved solids are often measured with a conductivity meter, and again you can just do an evaporation step, which if you've got a certain amount of water and you weigh the amount of evaporate that's left afterwards, so whatever residue is left in the evaporating basin, it gives you a measure of how much total dissolved solids. It's not identifying what those ions are, it's just telling you how many there are. Less than 500 is parts per million is considered to be fresh water. The Sydney water supply is considerably less than that, between 40 and 100, and seawater is 35,000. So you can see a very big difference in those. Water hardness is a titration method, EDTA. You guys actually saw that at the University of Sydney when you had a look at that day and the titration that was carried out there, just to identify the amount of ions that are contributors to hard water, and the equivalence measure is for calcium carbonate. And again, you can see less than 75% is what we want for soft water. If it gets above 150, then it's considered hard, and our Sydney drinking water, very low. Turbidity with a turbidity or Secchi disc or a turbidity meter. Again, if you can filter the suspended solids, so here we're talking about suspended solids as opposed to dissolved solids. When you're looking at this particular one, you're looking at nephelometric turbidity units. That's the NTU, nephelometric turbidity units. You need a very small number of those for the water to be potable, and once it becomes much bigger than about approximately equal to or greater than 20, it's no longer suitable for water life. So it has to be down below 20 for that to be the case. Acidity, we want to make sure the acidity is around a 6 to 8 range, and I shouldn't need to tell you that you're looking at a pH meter or universal indicator paper to measure that. And then dissolved oxygen, we have the Winkler method, the Winkler titration, which is a back titration or testing with thallium oxygen sensitive electrodes. So there are actual oxygen meters you can talk about in order to measure dissolved oxygen. We want to make sure that good quality fresh water has around about 9 parts per million dissolved oxygen, and polluted water very, very low. So this is an important one because dissolved oxygen, the lower it is, the worse it is in this case. And BOD is basically just a comparison method. So we need 2 samples, one which we're going to do straight away and one which we're going to leave for 5 days in the dark, and then the difference is the BOD. And so you can see here a few measures that give you a good indicator of what's good. Unpolluted natural waterways 1 to 5, polluted ones are more than 5, treated sewage 20 to 30, and raw sewage 150 to 300. So these high figures are very important when you get questions around the concept of BOD, telling you that maybe you're around agricultural areas where they keep livestock perhaps, and some of the waste from the livestock has been emptying straight into the waterways. So these are the tests that we look at to determine the quality of the water. Thanks for watching.